Hello and welcome to your science lab. My name is Mr. Trevelyan, if you haven't met me before. I'm one of the science teachers at SLA, and today I'm going to be leading a lesson with you about, just to recap, everything that you should have learned this term about magnets. So allow me to share my screen. Please bear with me. Okay, so you should now be able to see a PowerPoint slide with Wednesday, the 2nd of December, today's date in the top right corner. What I want you to do is to pause the video and do all of the exercises in the yellow box in the middle of your screens. So read through, pause the video now, and follow those instructions. There's also an extension at the bottom. Okay, welcome back. You should have got some pen and paper and a stopwatch, and having written the LQ at the top of a piece of paper. So, yeah, in terms of that extension, I just want to really try and make sure that everyone doesn't lose touch with science when we're at home, we're not coming to school. So here are some of my ideas for that extension. The things we can do with science at home. Experiments, I've written down some things there. Documentaries, I know a lot of us these days are watching a lot of Netflix, but it can be very educational, such as Attenborough documentaries and YouTube channels. They really are the most fantastic resource, some of them. I just got done watching a video by Kurz Gesagt. It's written down for you there, which is a YouTube channel. It was talking about what the Earth would be like, what planet Earth would be like if it kind of got shunted away from the solar system and away from the sun, and what would happen on Earth and why that might happen. And there was some really great scientific ideas there, which were explained in a really fantastic way. So yeah, those YouTube channels I'd highly recommend those of you who are interested in science to check out, just to keep up the science knowledge in the background while we're at home. So this is weird, isn't it? How this is going to work is I'm going to make you're going to make notes as you watch me talking. I'm going to bring them back to your science teacher when we come back. Pause the video when I tell you, or if you get stuck, if you're not sure about what I'm talking about, just pause, rewind, listen again carefully. And if that fails, then just Google the topic in question to try and bring up your understanding. So I'm going to be talking about magnets, our first, the first topic you should have covered this term in science. And essentially what the lesson is going to look like is a lot of me talking to start with, and I'm going to give you some activities to go away with at the end. If you're finding it easy, just skip forward a little bit. So overview of today: what are magnets and magnetic fields, and how do they work, which is something we call domain theory. So first line, magnets. Magnets are objects with a magnetic field, and magnets attract the ferromagnetic metals. Those ferromagnetic metals are iron, cobalt, and nickel. I put down their periodic table entries there, which we should have met last term. So yeah, just summarizing the difference between ferromagnetic and magnetic below. Magnetic means that it's a magnet, which means it creates its own magnetic field. It means it has this influence on other objects. And ferromagnetic is iron, nickel, and cobalt, which means that they're attracted to magnets and can be magnetized, but they're not actually magnets themselves. They don't have their own magnetic fields unless they're magnetized. So, for example, those iron nails at the in the image there, those are ferromagnetic because they're affected by the magnet. But that red thing at the top, that's a horseshoe magnet, is creating a magnetic field, which is having the effect on the nails. If the magnet wasn't there, those nails wouldn't be touching each other. And that's just a little image of some iron filings. Iron filings made of iron, tiny little pieces of iron, and then when we scatter them around a magnet, we can we see this nice pattern. We also need to know what poles are. Pretty easy, but it's just the ends of a magnet. I think we all kind of know this. And attract means that it's a pulling force. It means pulling things together. And unlike poles, so north and south poles, they'll attract each other. Repel, on the other hand, means pushing force, and you can see that on the right of that diagram. If you try and put two like poles together, i.e. two poles which are the same, south and south, or north and north, those poles are going to repel each other. It means they're pushing away. They don't want to touch each other. Magnetic fields, I've thrown around that word magnetic field, and all magnets have this, but we need to know kind of what it means as well. And a magnetic field simply is just the area over which a magnet exerts its effect on I should say, ferromagnetic objects or other magnets. So whenever you come within this magnetic field, that's when the magnet starts doing this invisible stuff, like attraction or repulsion. So we can actually show magnetic fields with field lines. Those are your iron filings again. And do you see how they kind of assemble into this pattern? We actually draw that, and that's how we represent the magnetic field, as arrows going from the North Pole to the South Pole in a pattern that looks like that. We call that a dipole pattern. A compass can actually be used to identify these magnetic field lines. What am I talking about? Well, a compass is just a magnetized needle floating about on the top of some water. So magnetized just means it's affected by it's got a partial magnetic field, and because it's so lightweight, the needle is going to swing to line up with the magnetic field which it ends up in. And you're just going to watch that video. This might not make much sense at the moment. You're going to watch a video that I've attached entitled "Using a Compass to Plot Field Lines." You're going to write that as a subtitle and write a method for this practical. So can you pause the video now, check out that video, write a method, and yeah, come back to me when you're done. Welcome back. Field lines. Yes, yeah, so we know what field lines are, and they're drawn as arrows pointing from the north to the south pole. When those field lines are really close together, the magnetic field is the strongest, and when they're further apart, the magnetic field is weaker. So that diagram at the bottom right, that's just showing a magnetic field and the field lines around it, north to south, and that's it. They're continuous, remember. So where the diagrams end, where the arrows stop at the end of the diagram, they actually go all the way around to the south pole, but we can't see it because the picture's too small. So your task for 3 minutes, I want you to pause the video. You're going to copy that diagram down of the bar magnet's magnetic field with the subtitle field lines. And on that diagram, I want you to label the field lines, where the field is the strongest and where the field is the weakest. Remember, close equals strong, far equals weak. Welcome back. So on to domain theory. And domain theory is really talking about how magnets work, right? We've accepted that magnets have these invisible effects, this attraction and repulsion on other objects. But we need to know kind of the idea why this happens. And the answer is domain theory. So ferromagnetic materials such as iron, nickel, cobalt, and steel. Steel is an extra on there, but it's ferromagnetic because it contains a lot of iron, so it's still not just iron there. But these things which are affected by magnets, why are they affected by magnets? Because they contain these small little regions called domains. And on that diagram at the bottom of the screen, we've shown the domains like tiny little magnets. And normally in an unmagnetized material like an iron nail, the domains are just pointing around in random directions. So that's the same as what we've got in the diagram there. These ferromagnetic materials, they've got tiny little regions called domains. They're like tiny little magnets, and then when it's unmagnetized, the domains are pointing in random directions. But what happens when we magnetize and demagnetize a nail? Well, that's something we can explain here. So magnetization occurs when all of the domains are pointing in the same direction, and this can be achieved by stroking the material with a permanent magnet. So if you look on the right-hand side, well, on the left-hand side, sorry, we've got the same unmagnetized material. Those domains are pointing every which way. They're not aligned, right? They're pointing differently. They're randomly arranged. However, if I were going to stroke a permanent magnet, like my bar magnet, across let's call it an iron block, then what happens? Well, if you look on the right, those domains are lined up in series. They're all facing the same way, right? All the north poles are at one end, and all the south poles are at the other end. And when we get that alignment of all the domains, we actually it becomes a magnet. It's been magnetized, and it creates its own magnetic field. So we're temporarily turning that iron block into its own magnet. And you can actually show that by, if I had an iron nail, I obviously can't show you here, but if I had an iron nail and I stroked it with a magnet, a strong magnet, and then tried it on a paperclip, it would actually pick up that paperclip. And you might have actually realized that when in a practical, you might have done this term. I'm not sure. However, demagnetization, what's that? Well, it's in the name, you can kind of guess. If magnetization is turning it into a magnet, demagnetization is stopping it from being a magnet. And that occurs when the domains are shaken back into random directions. So there's my magnetized iron block on the left-hand side. And I've bashed it with a hammer and I've put it up to a really high temperature. And the reason heating it up and hammering it will demagnetize it is because it shakes those domains, those areas, those little tiny magnets inside the magnet into random directions, right? So once they're in random directions again, that means the magnetic field is destroyed and it is no longer a magnet. Heating, by the way, only will shake up the domains because it gives all those particles more kinetic energy. They're shaking around even more, and that causes them to get a bit excited and point into random directions again. So that's just the essence of domain theory. So for 5 minutes, in full sentences, I want you to answer those questions. Have a go answering those questions. If you're not too sure, rewind me what I've just said and try and try and answer them in your own time. I wouldn't spend more than 5 minutes doing that. Yeah, remember if you're stuck, just look it up, look up domain theory and see if that makes more sense. But yeah, pause the video now. So, well done. You've made it nearly to the end, but you've got 15 minutes of work left. I'm sorry to say, but these final tasks, they've been differentiated into bronze, silver, gold, and extension. And those extension questions are really hard. And I'm not really expecting anyone to actually do them unless you want to prove to your science teacher that you really are thinking about the bigger picture. Anyway, so it should take you 15 minutes and I want you to answer in full sentences. But if it's easy, please move on to the next level, because the easier something is, the more boring it is what I usually find. But yeah, there's the warning again. The extension ones are very challenging. Don't worry if you don't understand them. So here's the bronze. Question 1, define these words in full sentences. There they are. Don't know why it's appearing like that. Number 2, you've got to answer that question. And number 3, you've got to answer that question. So if you want to try the bronze, pause the video now, have a go for 15 minutes. Remember, if you're finishing on to the silver, which is about to appear now. So silver, we've got more words to define, but this time I want you to draw diagrams to explain them where you can. So magnet, ferromagnetic object, attraction, repulsion, and magnetic field domain as well. And magnetized, excuse me. So for silver task, I want you to define those words with diagrams and then answer those questions from 2 to 5. Question 5 is a fun one. Have a look on YouTube if you're not sure what that picture's trying to show. So pause the video now if you're trying silver. Finally, gold. We've got some more words to define. Where are they? Ferromagnetic object, domain, magnetized and demagnetized, same as silver. And then you've got more questions to answer. Remember, if you're finding these still easy, then please go on to the extension ones by all means. And if you're not finding it easy, go back to silver, make sure you understand it all. And failing that, go replay my voice as I'm trying to explain it, or Google it to try and make it clearer. So pause the video now for gold. This one's a little bit more challenging. And finally, my extension task. You really are brave for even reading these. But these are just, maybe just read them just for as things to consider. So question 1, what is a domain? Who knows? You will soon. Number 2, why are those 3 ferromagnetic metals, iron, nickel, and cobalt, all lined up next to each other in a periodic table? Who knows? Number 3, why does the Earth have a magnetic field, and does it matter? And number 4, kind of moving on to a future topic, but what is an electromagnet and how does it work? So those are my extension questions. So I'm going to stop sharing my screen now. I don't know. Am I back now? Can you see me? Yep, well done for making it through this lesson. I hope we're all safe and well. We're staying positive and we're testing negative. And yeah, good luck with the lesson. If you're not sure, why don't you yeah, just replay that video and until it makes more sense to you. So there you go. Enjoy.